Log on, tune in, find out. Another good idea from Cambridge.
The Gothen that he's going to talk on representation of surface groups and Higgs bundles.
Thank you very much. So, good morning. Just let me thank Letitia and the other organizers for inviting me to speak. So, so I'm going to talk about surface group representations and Higgs bundles, but maybe that should be really Higgs bundles and surface group representations, because at the end of the day I'll focus more on the Higgs bundle side of the picture, even though the plan of today is in fact going to be trying to explain to you how to get from surface group representations to Higgs bundles. So I hope you'll bear with me, because there won't be much algebraic geometry in today's talk. Anyway, so just before getting going, I'll try to paint here the big picture, a reasonably sized picture of what I'm going to do. So, here's our surface, genus G. It's closed, oriented surface, and the surface group is just the fundamental group of such a surface. So, well, we all learn that learn in basic topology that the fundamental group of such a surface has two G generators, subject to the single relation that the product of the commutators of the generators is the identity. Okay. So this is the one main character, and the other main character here is some real reductive Lie group. I'll write down my definition of that in a minute. So, by a representation of this group, fundamental group of sigma, I just mean a homomorphism from pi 1 of sigma 2 into G. Okay, so if G is a linear group, of course this gives us a representation on that vector space of which G is a linear group. Okay. Over here on the other side, we have some guys which I might call G Higgs bundles, and so the main aim of everything is to say, why is studying this kind of thing really, or how can we study these representations of the fundamental group of the surface using these G Higgs bundles? Okay, now there's a very precise correspondence that I'll get to. And it goes via this intermediate kind of objects that I might call harmonic bundles, more differential geometric objects. So the correspondence goes like this. So today I'll mainly talk about this correspondence. On Monday, I'll talk about this one, and maybe I'll also talk a bit more about G Higgs bundles, and lecture 3 will probably be down here most of the time. Okay, so that's the general plan. So let me get started then. So Okay, so what is this real reductive Lie group? So I don't think there's any unique definition of what a real reductive group is, but I've seen many different ones. So one possible way of thinking about it, which is not the most general, maybe not the best way, but let's just say that one way for you to have something to think about is just to think of a real form of the complexification of a compact group. Okay, so this leaves out some relevant and interesting cases, but anyway, this is one good thing to have in your mind. Anyway, there are many other ways of defining this. One, whichever way you go about it, there's a series of data that you can that you actually need to fix about this group to get this whole theory going. So, and you could actually take this fixing of this data as your definition of a reductive group. So, anyway, first of all, we need a maximal compact subgroup. Let's say, so we need also a Gothen involution on the Lie algebra of G, which gives us a decomposition of the Lie algebra of G in the Lie algebra of H and some complement that I'll call M. So these are the plus minus 1 eigenspaces of this involution. Need also I need an ad invariant non-degenerate bilinear form B on G such that this form here is a negative definite on H and positive definite on M. So if your group is semi-simple, you can just take the killing form for this form. Okay, so it's some sort of, think of it as some sort of extension of the killing form on the semi-simple part of the Lie algebra. Okay. So the final piece of data I need here is to just note that if we look at the adjoint action of the compact group H, or the restriction of the adjoint action of G to H here, then it respects this decomposition. So in particular, actually, H acts on this M. Let's call this the isotropic space. Just so we have H2. Let's say M. Just so if I take an element G here, just takes the adjoint action of G and restrict it to M, and that's a map from to M. Okay, so this is kind of the general data I need. I won't need all of it right away, but at various stages I'll need all these pieces of information about my group. Okay, so the next thing I want to introduce is the character variety. Okay, so that's just going to be the space of equivalence classes of these representations. Okay, so let me maybe use this notation in B of sigma G. By definition, space of homomorphisms of the fundamental group into G. And then if we think of the case of just a linear group, of course, we should consider two homomorphisms as equivalent if by a change of basis in our vector space, one can be transformed into the other one. So that just corresponds to acting by conjugation by the group G here. Okay, so this is the conjugation, overall conjugation action here I'm dividing out by. So if you see what kind of structure should this have, so if G is, for instance, an algebraic group, well, at any rate, let's just, for the moment, before we divide out here, just notice that what is a homomorphism? It's just saying where those two G generators go. Okay, so just this space of homomorphisms here can actually, at least if we choose generators of the fundamental group, we can embed it into this Cartesian product of G by itself 2G times. Okay, so this is just defined then by that polynomial equation up there. So that's a nice analytic variety in here. Okay, and then you can try to make this quotient depending on the nature of the group G. You can be more or less successful in making this quotient, but at the very least we can certainly look at this as a topological space. Okay, in general it's had to do much more, some sort of analytic space maybe. There's a problem here with this quotient, of course, because you won't get a nice topology on this in general. So you should actually restrict here to what's called reductive representation. So let me put here a little plus. So actually, this plus is supposed to mean that we restrict to reductive representations. Just meaning that there's a Zariski closure of the image of the fundamental group inside G is reductive. Okay, and with that we get a nice Hausdorff quotient. Okay, so that's a small technical point. So I forgot to say, so please interrupt me, okay, if you have any questions.
Can you explain why you get a Hausdorff quotient with that?
Sorry, say that again?
Why do you get a Hausdorff quotient with that?
Wow. Well, you have to. What you need essentially is you need the orbits to be closed, right? And that assumption gives you that.
I'm sorry, what the Zariski closure means? Because here it's everything real.
Yeah, so you should think of this as in a real sense. So, yeah, it's definitely the real Zariski closure there. Yeah, I mean this. There are other ways of defining this. You could think of taking the induced. So if you take any representation there, any morphism, you get an induced representation composing with the adjoint representation. Okay, so that gives you a linear representation, and you can ask for that to be completely reducible. Maybe, Okay, so in order to get over to sort of differential geometric world, let's try and get into let's try to formulate this in terms of flat principal bundles. So let me take here the universal covering of our surface. So this is just this is I have the fundamental group here acting as covering transformations, and it's simply connected. I guess at some point at least we'll start assuming that G is at least 2. So anyway, you can think of this as anyway, unless sigma is actually a sphere, this is just a contractible space. Okay. So out of out of a representation, we can build a principal bundle. So let's define E rho to be universal coupling acted on by the fundamental group, and I'll act here on my on my group G via the representation. Okay, so this is just the quotient of the, very much like we saw in Thomas' lecture. So we can actually think of this universal coupler just as a I1 sigma principal bundle. We may have to turn the left action into a right action in order to do that, and that's the idea. So we get a nice bundle here over sigma. So this is a G principal bundle. And just act by our group here. And like taking the trivial G bundle here and then making some identifications. Okay. Now the fact that our principal bundle comes from, let me try and like here. So here's sigma and here maybe some layers of sigma tilde. The fact that our principal bundle comes from a representation of the fundamental group makes it a very special one, namely it's a flat bundle. So what does that mean? So, so one way of saying it is that we can define it by locally constant transition functions. Simply because, well, if we look at these layers here, it's trivial over each of these sheets of the covering. Another way of saying it is that we have a flat connection. Let me, before saying flat, let me just say we should briefly, before explaining that, connections in principal bundles. Okay, so we have in general some principal G bundle E over our base manifold sigma. That means that any fiber here over, so let's take here point x, we have some fiber EX, and as soon as we choose a point here, the fiber gets identified with the, choose a point here in the fiber, it gets identified canonically with the group. Okay, that's what Thomas told us. So therefore the vertical tangent space here gets canonically identified with the Lie algebra. So can be identified with the group, but in a non-canonical way. So we'll have to make a choice here. Let me indicate this vertical tangent space like this, TB E of E. Okay, so it's like tangent space along the fibers. And the connection is just a coherent way of choosing complements inside the tangent space to all these vertical tangent spaces. So choosing a horizontal subspace. So
convenient way of doing that is to say, okay, let's take a linear map from the tangent space at E to E to G. Let's require that this linear map be the identity on the fiber here, because the fiber here is really canonically identified. Let me put equal to G once we've chosen the E. So it restricts to the identity here, and the complement is the kernel. So it's really just a splitting of this inclusion. So we'll have this canonical inclusion, right? And the connection is just a splitting, this horizontal subspace here, is the kernel of B. And then we want this done in a way that is equivariant with respect to the G action. So the connection is actually a one form on the total space of the principal bundle with values in the Lie algebra, satisfying that so that B is just the canonical identification. Let's say it like this. Okay, and it's G equivariant. So this is what a connection is. Why is it useful to have connections? It's because you can, well, there are many ways they're useful, but one way is that you can differentiate sections of any associated bundle to this principal bundle. So, so if V is some representation of G, we have this associated vector bundle, as Thomas explains to us. So a connection gives rise to covariant derivative in dB of sections of E, so one forms with values in EV, so one forms on the surface. Of course, we can always take a section and just differentiate it, but the problem is that put it like this. Yeah, so the point is here that sections of this associated bundle, we can think of them as G equivariant maps from the total space to V. Okay, so we can differentiate these guys. The problem is to make them descend to one forms on the surface. But if we have here a tangent vector to the surface downstairs, this complement lets us lift it. So that is why we can then get this operator here. So I should perhaps put here sigma. Okay. Right, so that's one point about connections. Let me just also notice that given a connection, there's an associated curvature which in some sense measures the failure of differentiations in different directions to be a commutative operation. So it's a two-form which can be given like this. Actually a two-form on the surface. Values in the adjoint bundle. Okay. All right. So if we go over here and look at our construction of our principal bundle here, that so we have here these this universal cover. So we have the sheets of the covering. We have these copies of G, and then we just identify them using the representation. So it's of course easy to find horizontal subspaces because we can just take the bits that are tangent to each sheet. Okay, so we actually get a connection, and it'll be flat. So just because the fact again here that we are like this means that locally we are in some trivial product situation. Okay, so differentiation in different directions will depend on the order in which we perform the differentiations. So so we obtain then using horizontal subspaces, a flat connection. So a connection, let me say connection B in E rho with curvature 0. So a connection with curvature 0 is what's called a flat connection. Okay. Okay, so let me just schematically put it like this, then what we obtained. So to these representations we obtained the rho, say, flat bundle, and then we need to observe that this correspondence can be inverted. So if you have a flat bundle, you can take the holonomial representation of the fundamental group. So whenever you have some loop here in sigma, you can just take the holonomial of the connection. So that means just taking a section along the loop, which is covariantly constant, and that gives you a transformation of the fiber. So the holonomial. So the connection is B. Curvature 0. Holonomial of B. We'll take you back and give you your representation back. Okay, so I just want to write down then this correspondence I tried to outline here as a correspondence between, on the one hand, the character variety there, so representations up to isomorphism, and on the other hand, flat bundles up to isomorphism. So if you
What does it mean that you came from a reductive representation?
Here, well, here for this you didn't need a reductive representation.
But if you're going to use that thing, then what does it mean?
Okay, well, in a sense it doesn't mean, well, let me put it like this. I'm going to say that the connection is reductive if it came from a reductive representation, okay? But yeah, I mean, I don't think on this side that there's a much better way of saying what does it mean, okay? I think, in a sense, it means that the holonomial representation of the flat connection is reductive. So that's obviously in a sense doesn't tell you much more. But I mean, to put it in a different way, you could say that most representations are reductive. If your group is compact, all representations are reductive, so you don't need to worry at all. So consider this just a technical condition that you need to make the distinction. Okay. All right. So in order to write down conveniently the correspondence here at the level of the character variety, over here on this side. See, in the end, I wanted to explain things with connections, okay? But a connection is something that lives on a bundle. So I want to fix a principal bundle, and then I want to look at all connections on that. So it turns out that it's convenient to fixing. See, what is fixing a principal bundle? So remember, we're always in the smooth category today. So fixing a smooth principal bundle is really just giving its topological class. So here, I'm not sure I set this, and it's not always necessary, but anyway, let's assume that G is connected now. Because yes, definitely that makes life easier. Then let's take the universal covering group. we have an exact sequence like, have a projection down to G, and we can identify the kernel as a fundamental group of G. So if you think of a bundle, of a principal bundle, as we saw previously, as some element of this first cohomology set of sigma with coefficients. Let's say smooth G values, the sheaf of smooth G valued functions on sigma with that's it. Okay, so think of an isomorphism class of a principal bundle as an element in here. Then you can consider just about make sense of the, because this group is abelian, so you can make sense of the co-boundary associated to this sequence of sheaves, and that'll take you into the second cohomology with coefficients in pi 1 G. So we get a class that I'll call C of E, which is just a co-boundary of E. Of course, this is just pi 1 of G, which is again the same as pi 1 of the maximal compact H. Okay, so this gives you some topological invariant, and then if you think for a little bit, it can be proved that actually that classifies the smooth isomorphism class of the bundle. So the topological or the smooth classification of principal G bundles is a discrete problem. Okay.
So why is C infinity G there?
So this, so this is the way you get to this first cohomology set is by taking transition functions, right? So for now, I'm not thinking of the bundle as being flat. Okay, I'm forgetting that it's flat. I'm just taking any C infinity principal G bundle. Okay, so it's there because I'm working in that category. So maybe I should say C infinity sigma G or something. So it's a sheaf of smooth functions on sigma with values in G, and the co-cycle is one for that sheaf. Okay, so then you can take as a proposition that E1 is isomorphic to E2 if and only if they have the same class. Okay. As C of E1, C of E2. Okay. Okay, so for some D in pi 1 of H, which is the same as pi 1 of G, let's fix E with C of E equal to D. And then the correspondence here has from global version. So if I denote by, let me see, I did my, so let me take, so I have my space here in B sigma G, and let me now take let me take the subspace here of representations such that the associated bundle has class D. So this is going to be, by definition, rho such that C of E rho is equal to D. That is going to be via these constructions identified with the set of B. So a connection on E with curvature 0, and here I should probably also write reductive connection, just meaning that the associated representation, as I said, is reductive. And then, so we divide it out in the definition of this. Here we divide it out by the action, so here we have to divide out by isomorphism of flat bundles. So let's just say iso there. So let's give this a name as well. Let's call it N G, and since we fixed the invariant topological invariant in D, okay. So we have a fixed bundle E and we let the connection vary. Okay. So you can see this, actually this identification here, just sort of a non-abelian version of de Rhams theorem for first cohomology, right? If G is just an abelian group, say complex numbers or rational numbers or real numbers, what is this? This action by conjugation doesn't do anything because it's abelian, so this is just homomorphism from the fundamental group into, say, C, so that's first cohomology group, right, of sigma. And over here, the flat connection is actually just going to be a flat, going to be a closed one form. And this isomorphism, if you think about it for a second, just gives you. Yes? Assuming light is on. You don't hear me?
Not very well.
Okay, sorry. I'll try and speak louder, maybe. Some noise is coming out. Okay. All right, so let's see. So far we didn't do, in a sense, very much. We just translated representations of the fundamental group into flat bundles. So let me now take the next step and let's try and get on to the harmonic bundles. Okay. So the idea is to try and throw more and more geometry here at the problem. So let me make the following definition. A metric in principal G bundle E is a reduction of structure group to the maximal compact H. Okay, so for instance, if your group G is the general linear group over C, then the maximal compact is the unitary group. And if you think of it as Thomas explained to us that we could the bundle of frames of a vector bundle, this reduction of structure group just chooses you the sub-bundle of unitary frames that then defines yourself a fibrometric in the associated vector bundle. So that's the reason why you call it that. I should say that my reductions are going to be reductions to subgroups. Okay, so you need the general setup that Thomas Gomez was talking about. Okay, so you can think of this as a section of E mod H. So, in the notation of Thomas E G H, so it's just picking out, as I said, in each fiber which is G, it's picking out a copy of H. Okay. So let's note that if I started with a flat bundle, so if E is equal to this E rho, then in fact such a thing, so if this is the case, then such a thing corresponds simply to an equivariant map from the universal cover to G over H. Equivariant. Okay. This is because this space here can just be viewed as sigma tilde cross pi 1 sigma G over H. So thinking in terms of principal bundles, A section of the principal bundle is just a map from the total space. A section of an associated bundle to a principal bundle is a map from the total space of the principal bundle to the fiber space, which is equivariant. So this is exactly the correspondence. Can you see here? There's a little notice here saying, huh? It's okay? All right. Better move over here. Okay, so clearly picking a metric is a good way of doing geometry because after all, in geometry you're supposed to measure things as the word says. So now the question is, if we have a flat bundle like that, is there in some sense a best choice of metric? So is there in some sense the best choice of metric in rho? And the answer is that, well, one possible answer is yes, there is. You can try to minimize the energy of the metric. The energy. Okay, so I'm going to write down what is this energy of the metric, and then I'll explain the ingredients afterwards, because I write it doesn't make sense then. What we do is we take our map there, H, and take its norm squared and integrate it over the surface. Okay, so in order to make sense of this, there are several things we have to make sense of. So let's note that so what is dH? Yeah, first of all, so first let me say that if you think of the metric as just a map from the surface up to that quotient space there, let's see. Yeah, so we think of the map here. So we have derivative as a map into the tangent space here at hx to over h, but then using the connection we can actually map down to just the vertical piece of this tangent space. Again, in a similar way to what I was explaining before. So this is what I call big DH. Okay, so we can use D to get down there. Essentially, if our flat bundle were actually a trivial bundle, see our metric would just be a map to this homogeneous space, and it would just be taking the derivative of this map really. Okay, so that actually makes sense because the bundle is flat, even though it's twisted. Okay, so we can do that. Of course, to integrate, I need a metric on the surface. So I need a metric, Riemannian metric on sigma. So we need here Riemannian metric on sigma. It turns out that this functional here actually only depends on the conformal class of the metric. So conformal class of metrics.
Of course, we also need to take this pointwise norm there that we integrate, so we need an inner product here on this tangent space, which is just we need a metric here on the tangent space, so metric on G mod H, but that's easy because the tangent space to this is just this M space. We can just use that bilinear form that I chose, that we had the form B. I think I called that B as well. That was a bad choice, huh? Okay, so anyway, use non-degenerate bilinear form on M inside G. Noting that this M was just really tangent space to G over H at, well, some point, let's say 1. Okay. All right. Or at least, well, okay, minimize a second. All right. Okay, so so this is clearly a variational problem. Okay, so you should try and work out what are the Lagrange equations for this variational problems, and you can do that. So let me write down this. So d naught plus star dh equal to 0, where I should explain what I mean by this d naught plus star. So let's notice there's this dh here, so it just takes values in this vertical piece. So in fact, so it's a one form, and what it does is it takes values in the pullback by h itself of the vertical tangent bundle to e over h. That's where it takes values. So we could also look at omega 0, sigma of the whole same thing, and fact is that we can define a connection on this bundle over sigma out of the data we have. So G over H is a Riemannian manifold, so it has a Milik-Jupiter connection, so you can define a connection here. So use the Jupiter connection on G over H, and use also the flat connection B to get a connection in this bundle, and then you just take some formal should go down some formal adjoint operator here. Okay, so that's very briefly what this equation is. It's not so very important, the exact meaning of these operators anyway. Okay, they won't play for what I'm going to do any serious role, and we'll reinterpret this in a different way anyway in a minute. So just to write you down the equation. Okay, so now I can state the theorem.
So D star is the adjoint?
Yes, it's the adjoint, yes, you take some adjoint of this operator. Okay, so of course you need to introduce L2 metrics on these the spaces of sections and so on, right?
In case G is a circle, does this energy have some more recognizable,
Sorry, in case?
In case G is a circle, do I already know what this energy is? It's something that I may have encountered before.
In case
The strange
G is, well, in case G is compact, this is not really, there's no point in looking at this, right? Because H is the maximum compact. But say in case, let's see, so in case
if she is a real line, okay, this is just the usual derivative, and this is the adjoint, and at the end of the day, this equation here is sort of the adjoint after the usual derivative, so this just says that the Laplacian of h is 0, okay? So it's the usual harmonic map equation, okay? Yeah, I should probably have said that. Okay, so let me write the theorem which is due to independent Lee Donaldson, and for later I'll quantify this in a minute. Says that the representation rho is reductive if and only if the corresponding flat bundle E rho admits a harmonic metric. Okay, so, well, before, well, writing here proof is certainly an exaggeration. I'm not going to prove it, but just going to give you the vaguest of ideas. But anyway, let me just say that so Donaldson proved this actually for the case of surfaces and for G equal to SL2C, and whereas this was, let's say, general base manifolds and general groups. So, yeah. Okay. So, all right. Yes. So the point is, as I was, that this equation here is really the harmonic map, general harmonic map equation for this map H. So, so let's say that.
Sorry.
Yes.
Is it written dimension sigma is 2?
Sorry.
I'm just a bit confused. You say dimension sigma is 2, or is it genus, or what is it?
No, so the dimension. Okay. So well, it's a surface, so it's always two-dimensional, two real dimensions. So okay, it doesn't make much sense because I didn't talk about anything other than surfaces. The point is that you can set this whole theory up for general base manifolds, okay, and you can prove the analogous theorem in that case. So that's just what I wanted to point out. That's what Colette did. Okay. All right. So. This equation there, h equal to 0. We can think of that as, if we express that in terms of that h tilde there, just means that I can write this as h tilde equal to 0. So this is more like a map between manifolds, and this is just a harmonic map equation actually for this map between Riemannian manifolds. So this is saying that h tilde is a pi1 sigma twisted harmonic map. Okay. So that means that you can use the theory of Yields and Sampson that says that that explains how to find harmonic maps. So you might say you use this sort of twisted version of Yield-Sampson methods that works. Okay. Okay, I'm not going to not say much more about that. So one comment is that, so the difficult bit is to prove that if the representation is reductive, that you can actually find the harmonic metric, okay? And what you do is you solve some evolution equation for some arbitrary initial metric, and then at the end you are getting convergence to a harmonic map, because you write down an evolution equation and you solve that, and using these hypotheses you can make it work. So that's just some serious analysis that you can make work. Okay. whereas the other direction is not very complicated. Okay, so I think what I want to finish by doing in the last 5 minutes and just reformulate this a bit to set the stage for Monday. So okay, so let's say we have a reduction here. So let's say reformulation of this. Okay, so of course, so let's say we have a given reduction, a given metric, H. Okay, we can just look at the corresponding H principal bundle inside our G principal bundle, and that is just equal to pi minus 1 of H of 6. Okay, so these are just the H frames that you get like that. And now remember that our connection B here has a one form on E the values in the Lie algebra, so we can just call this I. So we can just pull this one form back to one forms on EH with values in G. So we take here I star of B lives in here. And then let's look at separately the paths that take values in H, the Lie algebra of the maximum compact, and this complement M. So, of course, this G here is H plus M, so I can write this as some A plus some theta, where in fact A is a one form on EH values in the Lie algebra, and of course that becomes a connection because it's just a restriction of a connection. On the other hand, the theta, it kind of lost its connection nature because we have here the algebra of G, and then we have in here H, and then we have the complement M. So in fact, if you look at what happens to this other bit, if you take some vertical tangent vector to EH and evaluate the theta bit, you just get 0, okay, because it was all over here in the A path. So therefore that's what's called a tensorial form, so that descends to one form on the base. So theta becomes actually an equivariant one form on the base, so that means that it defines now a section on this bundle EHM, where here, so this is the bundle which has fibers M associated by this restriction of the adjoint representation that I talked about in the beginning. So this is via this isotropy representation iota that I defined at the beginning. Okay, so we have, so just to sum up, given a reduction, our flat connection gets decomposed in an H connection and in some nice one formal values in M. And yes?
The letter A is in omega 1 of EH, and what's that letter then?
This is supposed to be some Gothic H, so this is the so this is the Lie algebra. Yeah, I apologize for my fonts. So it's the Lie algebra of the maximum compact. Okay. All right. So let's just. So let me just. Can I just take 2 minutes to finish? So okay. So let's remember that the fundamental equation here was F, that the connection B is flat. Okay. So if we try to express that in this terms of this data A and theta, well, so this is just dB plus 1/2 of dB. So we can split this two form into an h-valued pad and an m-valued pad. Okay, so that gives us two equations. So the h-valued pad says that dA plus 1/2 of theta bracket theta is equal to 0. And the m-valued bit is that d theta plus a theta is equal to 0. This has to do with h and this has to do with m. Okay. So if you know a little bit about connections, you see that this is just a covariant derivative associated to a acting on theta actually. So this we can write as dA of theta. We call these two 1 and 2. And then so this was the flatness condition, and then we can also reinterpret this. Where did it go? I guess I erased it. So the harmonic map condition up there. Yes.
The first equation there is the bracket of A as well. The curvature of A.
The curvature of, oh sorry, yes, absolutely. It's okay. Indeed. Thanks. Absolutely. Yes. Okay, and the second equation, so the equation, so this was here, and then also we have the equation that, so the d now plus star of h equals to 0. In fact, if you look at what all these things mean, you see that up to a scale of this, d napa is just the covariant derivative associated to a, acting on these one forms, and dh you can identify with theta. So this really just says that dA star of theta is equal to 0. So let me call this the third equation. Okay. So the upshot of all this then is that our character variety, so each point in the character variety for a fixed topological class, we can associate this pair A and theta, and now if we just change point of view a little bit, and instead of thinking of a bundle where we fix the connection and vary the metric, we can think of taking a bundle with a fixed metric and then using gauge transformations or using automorphisms on the connections. That's really the same thing. It's like, yeah. So we can altogether write down that our character variety M B sigma G can be identified with the space. So let's say fix EH inside E. The upshot is that we can think of this as the pairs A theta, which solve these equations. 1, 2, and 3. Modulo, let's say H gauge transformation, H automorphisms. So let's say the automorphism group of EH. Okay. So the harmonic map theory gives you an equivalence between the representations of the character variety here and the pairs A theta that satisfy this flatness condition and the harmonicity condition. Okay, so I'll finish here, and then on Monday I'll try to explain how you go from here to G Higgs bundles and get back into the world of algebraic bundles or holomorphic bundles.
Questions?
Oh, I was confused by that statement you made at the end about instead of fixing bundle and varying the metric. Can you just explain that?
Yeah. So we can. The idea is if you fix this bundle, okay, so the harmonic map construction, so it gives you maybe, if you take any flat connection, that gives you a different bundle, okay? So to bring it back down to the fixed bundle, you just take some isomorphism of that new bundle back to the old one, and you pull down the connections to that one, okay? So it's like, so it's like in a vector space, either you can fix the basis and where everything related in respect to that basis, or you can act with the group and change basis. I mean, it's like, okay, well, I'll take a little while to explain it carefully. Okay, but there's nothing deep in it. Okay, it's just really a question of the point of view.
There are no more questions.